Well, thank you again for inviting me to this workshop. And I will present this work. It is a joint work with my advisors, Pierre Chenet and Rémi Bardonnet. And I will start from the motivation behind this work is approximating quadrature rules that have this form, the integral of f against some weight function g and some measure d omega. So there are many framework. We have Monte Carlo methods, quasi-Monte Carlo, the zero of orthogonal polynomials, and recently there was an interest in determinantal point processes. And the question we ask is there can we give a universal analysis of kernel quadrature under DPPs? So I will briefly make a reminder on kernel quadrature, and then I will move to the core of this presentation. And at the end, I will try to give some hints on the idea behind the proof. Now, as usual, we have the same framework of kernel quadrature. We assume that we have an RKHS corresponding to some kernel K, and we assume that it is embedded in some L2 space for some measure d omega. And the slight modification we have is that we tolerate some degree of freedom that is expressed by this function g. So g is not necessarily uniform in our case. And it's very slight difference, and I will show you the why in later. And we can make the same upper bound on integration error using the product of the norm of f times the residual of the mean element by kernel translates. And we can define, as usual, the optimal kernel quadrature. That is, for a fixed value of g, we look for the optimal weight w. So it corresponds to the optimal mixture that is the interpolant of mu g. And it is also the orthogonal projection onto the subspace of kernel translate. So the question we ask is, can we give a universal way to define a configuration for optimal kernel quadrature? And the idea is to define a random configuration that give lower probability to this kind of distribution, this kind of configuration, and high probability for this kind of configuration. So we need some negative correlation property that is achieved by what we call determinantal distribution. So we will consider a new kernel kappa that is not necessarily the kernel of the initial kernel of the RKHS. Kappa could be different. And we assume that the diagonal is integrable with respect to d omega. And under this condition, we can prove that the function that is proportional to the determinant of the kernel matrix of kappa is a probability density. We can define a probability density using this, and we call it a determinantal distribution. So we will consider mostly two cases. The first one is projection DPP, and in this case, we assume that kappa is projection kernel for some orthonormal family in L2. And the second one in what we call continuous volume sampling, and is kappa is equal to k. So we will assume that k is also integrable with respect to d omega. And this is what we obtain when we simulate projection DPP corresponding to the Fourier family in the hypercube. And we compare it to two samples from the uniform distribution. You can see the difference is that we have less clustering, fewer clustering compared to the uniform sampling. So this is, we can see that we have some kind of negative correlation property. Okay, now there is a degree of freedom for we have a lot of choices for the projection DPP. As I have said, that we will choose kappa is equal to k, or kappa is a projection DPP. But in this case, we can choose a lot, many situations. We can choose V to be anything. So we need to specify the projection DPP. And we will start from the Mercer decomposition of k with respect to d omega that contains the eigenvalue and eigenfunction of the integration operator, big sigma. And we can prove something like a Mercer decomposition of the continuous volume sampling. It is a mixture of projection DPPs that have a normalization constant n factorial, and the weight is simply the ratio of the product of the corresponding eigenvalues by the sum of everything. Okay? And what we consider is the largest, the U, or the projection DPP corresponding to the largest weight in this sum. So we have now fixed this notation, and the main reason why we choose this one, because we can prove a theoretical result. So I will give you the result. We define Rn is the sum of the rest of the eigenvalues. And what we prove is that the expected value under the distribution of projection DPP of the worst case interpolation error. So here, G is spanning the unit ball of L2, is upper bounded by this quantity that contains Rn. And we have a polynomial on n. So if we assume that the kernel is smooth enough, we will have Rn conversion to 0 fast enough to get this conversion to 0. And in a recent development, we proved that we can get rid of this term. So the only thing we need to care about is this term, that is 4n power 2 Rn. Now, in the case of if sigma n is polynomial on n, or the inverse of polynomial, Rn is polynomial, but with a higher degree. Okay, we have n power 1 minus 2s. And when we add this n power 2, we'll end up with n power 3 minus 2s. And it's not optimal, as I will show you. But if sigma n is geometric, Rn is geometric, and we can see that we are almost optimal in this case. So the lower bound that we compare with has this following form, is that if we consider every subspace in the R-caches of dimension n, and we consider the worst interpolation error, it couldn't be below sigma n plus 1. So we need to compare ourselves to this lower bound, that is sigma n plus 1, and we can see that we are not optimal, but close to the optimality. Now, what happened for the continuous volume sampling distribution? So here it is volume sampling, and we have a different result. That is, we give the expected value of the interpolation error under volume sampling, and we prove that it has a tractable formula. So we express G in the orthonormal basis in L2, the orthonormal basis EM, and we have this spectral decomposition of interpolation, the expected interpolation error. It is the sum with this coefficient square times this coefficient that are the expected value of the embedding of the eigenfunctions. And we have this tractable formula. So it has this form. It is a ratio of two normalization constants. This the first one is the normalization constant of the volume sampling, and we only need the missing term is n factorial. If I will show you again, here is the normalization constant of volume sampling, and we have this in here without n factorial, and we have the same in here, but for another kernel that is the k, but without the direction m. Okay, we remove the direction. So we have this nice formula, and the question is, can we see something interesting about the rate of convergence of this epsilon m. And if we do it numerically, like we can approximate the ratio by truncating and taking sufficient big truncation, we can we see this phenomena that the epsilon m are ordered, and they are upper bounded by 1 plus b times sigma n, or sigma n plus 1, for at least 2 different settings in here, when if sigma m is geometric and when sigma m is polynomial. Okay, and the question is, can we prove this for this result in this under what condition we can prove such behavior of the epsilon m? So, and this is what we have proved, is that under a technical condition, we can drop it for the moment, we can prove that the largest epsilon, that is epsilon 1, is upper bounded by 1 plus b times sigma n plus 1. And you can check that we satisfy this condition for when sigma n is n power minus 2s, we give development for to satisfy this condition, and we have a tractable or an explicit formula of b that is simply 2s over 2s minus 1. So we have a very explicit result in specific cases, and also we can prove it in other settings, and this is the main interest behind this this kind of result, is that we have a universal analysis of kernel quadrature. So I will move to numerical simulations, and I will give you simulation in these cases when F is the periodic Sobolev space for 2 orders, and when F is the Korobov space of dimension 2, that is the tensor product of periodic Sobolev spaces, when F is the Gaussian space that is associated to Gaussian kernel in dimension 2. And we can compare all this sequences, continuous volume sampling kernel quadrature, optimal kernel quadrature. We may take an average on 50 samples, and in this case, we need to use a Markov chain Monte Carlo sampler, and we consider also projection DPP, again averaging on 50 samples, and in this case we have an exact sampler. We can use the leverage score quadrature that was defined by Bach, and in this case it corresponds to the uniform distribution, and we consider the setting where we remove the regularization. So in his setting, he need to add the regularization, but I plot the results without the regularization, and the uniform grid, and finally the Hartung sequence. Now let's start with the continuous volume sampling, and with with the empirical rates compared to the theoretical rates. Now, as I said, we use the MCMC algorithm, so it's an approximate sampler, but we can see that we have an empirical expectation that almost matches the theoretical rate or the theoretical result. For example, here we take G is the first eigenfunctions E1, E5, E7, and you can see how it corresponds. Now I will change the setting. I will consider the worst interpolation error. So I cannot calculate it in general, but I can calculate it on a finite set. So instead of considering the maximization on the unit ball, I will maximize on a finite set of the unit ball. And the cardinality is 64, for example. And here we consider the periodic Sobolev space, and you can see that the DPP, so we have a rate of n power minus 2s that is only different compared to the uniform grid. We have only a constant between the two, And here we can see uniform sampling or leverage score sampling that is slightly slower than the two. We can say the same phenomena for s equal to 2. We have a rate of n power minus 2s. So this I plot here the rate that is the power into the slope of the rate of the curve. And again, we can see that independent sampling doesn't give the best or slower rate compared to DPP and uniform grid. Now we move to Korobov space, so we will move to higher dimensional space, d equal to 2 and s equal to 1. And you can see here the uniform grid behaves as n minus 2s over d. So the scaling is, even if it starts better, but the scaling is not better than, get worse with the dimension. And we can see here for the projection DPP, it corresponds typically to the eigenvalue of order n. And we can see here Halton sequence behave better than the projection DPP. But in order s equal to 2, we have the same thing, but we cannot, I think, and I think we cannot prove this kind of high order rates for Halton sequence in this situation. And we can see that in the case of DPP, we always matches the eigenvalue of order n. Again, here we can see the interpolation error for different eigen functions. So every epsilon m is the interpolation error of the embedding of some function m, and we can see here what we call the initial error, and then it goes to the same curve that they coincide all in the same curve that is behaves like the eigenvalue of the integration operator. This is the same when we go to s equal to 2. We have the same phenomena, initial error and then decreasing to 0 at the rate of integration, the eigenvalue. And what is interesting is that you can see that in the case of the Korobov space, and because of the multiplicities that are due to the fact that we are in high dimension, the multiplicity of the eigenvalue 1 is 3 power d in here. So the more the higher is the dimension, the largest is the plateau of the eigenvalue 1, and etc. And we can compare this rate that was proved by Bach to the rates of Halton sequences, the quasi-Monte Carlo sequences. And you can see, for example, what we know is that the Halton sequence has a rate that is n power minus 2, but it can get a rate that is n power minus 2s when we optimize the weight. And this is also, for example, for high order digital nets, we have optimal rates that are almost optimal rates that are n power minus 2s. So we can see that this eigenvalue of the integration operator corresponds in this specific case to quasi-Monte Carlo rates, if you like. Now I will show you the last result. The last simulation is for the Gaussian kernel and for the Gaussian measure, and you can see here the empirical result, the expected value of the interpolation error corresponding to the theoretical rate, that is sigma n plus 1. And now I will move to just give you some hints why this could work well. So as I said, for the case of continuous volume sampling, kappa equal to k, we have a closed formula. And we developed this closed formula. We proved this this closed formula, and we developed it to prove that we have this scaling at sigma n plus 1. Now, in the case of projection DPP, we don't have a closed formula. And what we have, the idea was to upper bound this by some quantity that correspond to how close the subset, the subspace T of X of kernel translate to the subspace of the eigenfunctions. And the idea is to prove that there is a quantity that is have a closed formula and upper bound until this interpolation error. And now remember that we know that the projection or the subspace of the eigenfunctions has the optimal rate sigma n plus 1. We have this, we can prove this result. And the question is, since this subspace is optimal, how close is T of X to this eigenfunction subspace? And this is, we proved this result that gives a nice identity for the product of the inverse of the cosine of the principal angles between the subspaces, these subspaces, using the determinant of kernel matrix divided by the kernel kappa when kappa is the projection kernel. So we have this nice correspondence between a geometric quantity and determinant, and this has a closed formula under projection DPP. So I will just conclude. We give the theoretical analysis of optimal kernel quadrature under determinantal distributions, and we proved that continuous volume sampling has almost optimal rates, almost optimal theoretical rates, and we observe this optimality also for projection DPPs empirically. And the question now is, we know how to simulate a projection DPP exactly. We have an exact sampler for projection DPPs, but we need to, we don't know whether there is, it's an open question to design an exact sampler for continuous volume sampling. There are also questions like kernel specification of this kind of quadrature, and also to extend this kind of ideas to other problems like approximate kernel quadrature when we add some regularization or Gaussian processes approximation. And thank you for your attention.
Thanks for the nice talk. We can move to questions now.